I'm presenting this work titled GazeXplain, Learning to Predict Natural Language Explanations of Visual Scanpaths, on behalf of the authors Xianyu Chen, Ming Jiang, and Catherine Zhao from the University of Minnesota. Imagine you are driving through a bustling city at dusk, with your eyes scanning the surroundings for critical details like pedestrian crossings, brake lights, and turn signals. Human visual attention is a dynamic process driven by both the external world and the internal cognitive factors. Scanpaths naturally reflect how people strategically explore scenes and the decision-making processes to perform tasks. In this example of the driving and exploration context, the scanpath is guided by inherent tasks or dialogues like, does the person on the sidewalk appear to be walking? Specifically, one would start with a fixation on a car, then shift to the sidewalk to find a pedestrian, and finally confirm if the person is walking. Understanding the rationale of shifting gazes and translating it into explicit explanations can provide valuable insights into vision and cognition, and building this capability into machines will allow a range of interpretable AI applications. Earlier scanpath prediction models have been designed to take an image, sometimes with a task, as input to predict where and when people look during visual exploration. Although they have achieved reasonable accuracy, these models function as black boxes. They do not provide insights into the underlying reasons for these gaze shifts, making it difficult to understand why certain areas of an image attract attention, and they often struggle when scenes or tasks become complicated. To bridge this gap, we introduce GazeXplain with an integration of novel data and modeling efforts, which aims to not only predict scanpaths in varying scenarios, but also provides natural language explanations for the predicted gaze patterns. These explanations shed light on the rationale behind each gaze movement and offer a more interpretable framework for understanding and modeling the visual behavior. GazeXplain offers ground truth explanations for fixations across various eye-tracking datasets. Compared to previous image-to-language datasets, it has two key distinctions. First, we present the first natural language annotations on scanpaths, offering explanations for each fixation within the scanpath, rather than image-wise descriptions such as image captioning and visual storytelling. This granular level of detail offers deeper insights into the cognitive process behind each fixation. Second, GazeXplain comprises a wider range of visual tasks, including free viewing, object search, and VQA. This ensures the diversity of explanations, allowing models to be co-trained across multiple datasets to enhance their generalizability. GazeXplain also introduces the first model to predict scanpaths and generate natural language explanations simultaneously. The core challenge lies in translating brief fixations with limited context into clear descriptions due to the subjective nature of visual perception and lack of explicit semantic meaning. To tackle this, GazeXplain introduces a threefold solution. First, GazeXplain goes beyond conventional scanpath models by introducing a novel attention language decoder to bridge the gap between visual attention patterns and natural language explanations. Second, we propose a semantic alignment mechanism to ensure the semantic consistency between predicted fixations, explanations, and visual features. Finally, while prior studies commonly focus on single dataset training, we propose cross-dataset co-training, enabling models to learn from multiple datasets simultaneously and generalize well across different scenarios. GazeXplain demonstrates remarkable performance in scanpath evaluation metrics that capture spatial, temporal, and semantic aspects of human gaze behavior. In addition, its dominance in saliency metrics also indicates its ability to highlight visually important image regions. These comprehensive results suggest that GazeXplain can effectively capture the underlying patterns of human visual attention across diverse tasks and datasets, highlighting its robustness and generalizability. This qualitative example visualizes GazeXplain's scanpaths and explanations in comparison with the ground truth and the baseline model. For instance, when asked, what fruits are on the dessert on the left side of the photo, the baseline model attempts to describe fixated regions using a pre-trained blip captioner, and its descriptions often fail to align with the actual content, such as mistakenly identifying a plate of food with a fork and knife, when no such items are present. This is because the captioner and the baseline Scanpath model are trained independently. In contrast, GazeXplain accurately finds the cake on the left side, aligning with human gaze patterns in complex scenes. It also generates accurate and specific fixation descriptions. For example, it successfully distinguishes different types of desserts, demonstrating a robust understanding of the visual context due to the integration of Scanpath and language models. These results illustrate GazeXplain's ability to integrate visual exploration with semantic comprehension, resulting in more accurate, explainable, and human-aligned Scanpath predictions. Our ablation study highlights the significance of each component of the GazeXplain model: the language decoder for Scanpath explanations, EXP, the semantic alignment mechanism, ALN, and cross-dataset co-training, CT, and their combined impact on the model's performance in predicting and explaining Scanpaths. First, the integration of the language decoder alone into the model architecture results in substantial improvements in Scanpath prediction accuracy, even without semantic alignment. This suggests that providing natural language explanations for individual fixations enhances the model's understanding of visual semantics, thereby refining its predictive capabilities. Next, incorporating the semantic alignment mechanism further boosts the model's accuracy in both identifying the visual semantics of fixations and generating coherent explanations. These results emphasize the critical role of semantic coherence in guiding attention prediction models. Finally, our approach of cross-dataset co-training allows GazeXplain to learn from multiple datasets simultaneously and hence enriches the model's understanding, resulting in notable performance improvements across various datasets. These results demonstrate the effectiveness of combining diverse data for developing a more robust and generalizable model for Scanpath prediction and explanation. In conclusion, our work introduces a novel task that jointly predicts and explains human visual Scanpaths, providing deeper insights into visual attention processes. We contribute to this field in three significant ways. First, we define a new task that jointly predicts and explains where people look, offering a natural interface for understanding the underlying rationales for visual behaviors and reasoning processes to perform tasks. Second, we provide ground-truth fixation-level explanations across three public eye-tracking datasets, offering detailed insights into the cognitive processes driving gaze behavior. Third, we propose a general model architecture featuring an attention language decoder that not only predicts Scanpaths, but also explains them, bridging the gap between visual patterns and their semantic interpretations. Extensive experiments validate GazeXplain's superior performance in both Scanpath prediction and explanation tasks, demonstrating that integrating natural language explanations enhances the accuracy and interpretability of attention models. We believe that GazeXplain sets a new benchmark for developing interpretable models, paving the way for advancements in human-machine interaction and broader applications in language-driven environments. The source code and data are publicly available to encourage further research and innovation in this exciting area. For more details, please refer to the paper.